So I'll kind of pick up from what the previous talk's been talking about, so the transport and thermalization, but somehow focus here mostly on integrable models and using tensor networks to describe such systems, somehow highlighting so what features of integrability remain after we break those with some realistic perturbations. So integrable models are kind of special or so different from generic models because they have a macroscopic number of conservation laws. If we just kind of highlight here the Heisenberg model, which is one of the most paradigmatic models, it turns out that it doesn't have even just one family of these macroscopically many conservation laws, but actually several family of such. So these integrable models can be pretty rich. So in the Heisenberg model, we have, for example, a family of local conservation laws, which means that they are a translation invariant sum of local operators, or two more exotic families with quasi-local operators that have these exponentially decaying weights. So, and we'll get back to this model later. So two implications of the existence of this macroscopic number of conservation laws that seems quite important to me in the non-equilibrium dynamics are the following. So because of the existence of the conservation laws, these integrable models follow very different kind of, or show different equilibration after an excitation. So if you excite a generic system, what it will do is that at long times, it will essentially locally thermalize because the rest of the system can serve as a bath. While in integrable models, these additional conservation laws restrict the equilibration and will prohibit such thermalization and will instead kind of relax to so-called generalized Gibson samples. Second consequence of conservation laws is that such systems can show non-trivial transport phenomena if the current that we are studying overlaps with one of the conservation laws. In that case, we'll see ballistic transport instead of the usual diffusive one. And I'll first discuss the second point in the first half of the talk, and then in the second one, focus on the more on the equilibration. So if we go back to the Heisenberg model and look at the transport properties, because actually this model is one where very physical currents like energy current is one of the conservation laws and therefore shows ballistic transport in essentially all of the regimes. Now, also spin current, if we put such a chain in a magnetic field, will also be, we see that the spin current will be part of the energy current, and thus, if we put such a chain in magnetic field, we'll see ballistic transport also in the, for the spin or for the magnetization. And even kind of more exotically now, when we shut off the magnetic field, it turns out that the spin current becomes very rich. So it turns out that this spin current does, in that case, does not have overlap with local conservation laws. And it only has overlap with one family of quasi-local conservation laws in certain regime of this anisotropy being between 0 and 1. So summarizing it up, spin current in this integrable Heisenberg chain shows several transport regimes, so ballistic, diffusive, and in between the two, the superdiffusive one. And kind of the focus of this talk will be what happens to these different regimes once we weakly break the integrability. Yeah, as I just said, because that is, of course, very realistic. So in most of the experimental realizations, the integrability cannot be exact, at least not on longer timescales. Now, approaches to this problem are several. So let's say most traditionally, one could look at the optical conductivity and then determine the ballistic transport from the Drude peak and the diffusion constant from the kind of omega to 0 limit of the regular part. But that, of course, works only on small systems. Now, one approach that has been mentioned already in the first talk is using weak boundary driving due to coupling to baths, represented with some Limblad operators, and then use tensor networks to calculate the steady state for such setups. So in this setup, we, let's say, slightly preferentially flip the spins, let's say, down on one side and up on the other, and in that sense induce a spin current through it. Of course, now the advantage is that we can use kind of tensor, just usual TBD approaches and tensor networks to describe the steady state by simply vectorizing it and doing the time evolution. And then how the transport, how we extract now the signatures of different transport regimes from the current in this steady state is, for example, from the scaling of the current with the system size. So if the system is ballistic, so the current is ballistic, then the current should not scale with the system size that it the bulk that it goes through, because it's kind of ballistic, dissipationless. For diffusive transport, instead, the current should scale as 1 over L. And in between, you can also detect diffusive and superdiffusive regimes. So this approach was really pioneered by Marko Žnidarić, who's also here in the audience. And and we will kind of use that in the following to characterize the transport in our models. And the third approach is more kind of integrability based, and is using, or is seeing these integrable systems as being composed of quasi-particles whose stability is kind of guaranteed by integrability that then elastically scatter. And for Heisenberg model, actually now these different families of conservation laws map to different families of quasi-particles. So local ones map to magnons, quasi-local, one family of quasi-local to bound states of magnons, and then this third family of locals to some doublets with effective magnetic momentum. And in this case, let's say the Drude weight is calculated from the hydrodynamic theory by essentially summing over different types of particles and weighting, looking at the essentially contribution of v velocity, their effective velocity times charge squared contribution to the Drude weight. But this kind of works so very nicely only for purely integrable systems, while in the presence of perturbations, it's much harder, or it's essentially impossible or hard to use the hydrodynamic theory, and this is where numerics kind of proves useful. So we can look at different regimes, and we'll start here with maybe supposedly boring one, and that is the, let's say, the regime of diffusive transport, where one could think of, what can happen if the transport is already diffusive, even in the integrable case. But it turns out that this diffusion is quite, different, or is actually, let's say, caused by ballistic transport of these quasi-particles. Or at least in the large delta regime, one can see this as if the state is being composed of randomly oriented domains of up and down spins. And then the diffusion actually comes from the ballistic transport of quasi-particles through such a domain. So we see that we get diffusion from essentially dissipationless transport. So what happens when we add perturbation is that this nature of diffusion is drastically different and really dissipative. And this we can also see in the results. So when we look, for example, at the diffusion constant calculated from this open setup steady state, we see a crossover from the integrable one to let's say, a smaller value. So here, let's say, in that case, I added some integrability breaking perturbation. And as I increase it, and I'm plotting here the diffusion constant as a function of integrability breaking. And kind of what I see is that as I increase the system size, this crossover is becoming more sharp. And I actually anticipate that in the thermodynamic limit, the diffusion constant would kind of jump at an infinitesimal perturbation strength, as I said, because of this fact that the two, that the nature of the two diffusions is completely different. So this is kind of one of the first results that physical results that we got.
What is the value of delta here in this plot?
So in this plot was 1.5. So let's say, making link to your talk, okay, it's maybe where this approach is quite close to yours. And perhaps, I mean, maybe taking different approaches, we would get slightly different values of diffusion constant. But for example, we would at least anticipate that this jump, which is the main message here, is a safe conclusion.
But you expect that there to be a jump for any delta larger than 1, not just that? Because I thought the paper that you're referencing here is about like delta going to infinity.
I mean, in this paper that I reference here, they say that as delta goes to infinity, you actually have subdiffusive transport when you add perturbation. I actually have a slide here, because they say that when you in the delta to infinity limit, well, then with perturbations, you will have a diffusive transport through these random domains. So that in the delta to infinite limit, you actually expect subdiffusion, while at finite ones, this region is just finite in time, and you get diffusion at a different constant. I mean, at least we would anticipate this from these numerical results.
What is the exponent of the subdiffusion?
In their case,
yeah.
I don't know by heart, but it seems to.
I mean, does it depend on the coupling? I mean, is it variable or is it a fixed?
Coupling to?
Well, I mean, is it a universal exponent which has a set value, or can it depend on the parameters of the problem?
So, I mean, again, it's kind of only in this limit of delta to infinity. Yeah, and well, they would probably say that it scales like that with the square root. Yeah, another.
Sorry, you were expecting this jump at finite delta H or 0 delta H?
So in thermodynamic limit in the infinitesimal delta H. Yeah.
So the moment the model becomes non-integrable.
Yeah, because well, again in the thermodynamic limit, yes. All right. Now, then the second regime that we kind of attempted was this the superdiffusive one, which actually appears here in the isotropic point of the Heisenberg model. And our attempt here was to characterize how robust is the superdiffusive transport. So super diffusion in Heisenberg model actually, it's kind of, quite exotic or interesting. I mean, when you look into this quasi-particle picture, it appears that it's predominantly coming or caused by like these giant bound states. So like magnons with kind of towards infinity large number of bound magnons. And it can be seen essentially as some very slow like rotation of the vacuum state. And so somehow what we were then checking is how robust, and then the question is how much does such kind of exotic quasi-particles scatter on different types of perturbations. And for that, we introduced the perturbation which either, and yeah, to stress again, so this two superdiffusion happens only in the SO2 symmetric point of the model, of Heisenberg model and also other integrable models with extra isotropic symmetry. And then we added perturbations which either preserve or break the SO2 symmetry while breaking the integrability. And already somehow from the ED and finite magnetization, we saw these peculiar high diffusion constants for the perturbations that were preserving the SO2 symmetry, while, let's say here, as I plotted as a function of anisotropy, there was monotonous behavior of the diffusion constant for perturbations that broke the symmetry. So that is already the first kind of hint that something interesting is happening here at the isotropic point with very pronounced diffusion constants. Then again, as in ED, the magnetization was lowered. This peak was kind of going down and perhaps moving towards smaller anisotropies. But we thought, okay, at least from comparison of canonical and grand canonical results, this could be just a finite size effect. And indeed, when we repeated the tensor network calculation on open systems, we saw that this strongest diffusion constants was appearing at the isotropic point. And then again, moving towards smaller anisotropy as the perturbation strength was reduced. But is this also a finite size effect? So then we actually went to check how does this diffusion constant scale with system size. And what you see that it actually still grows with the system size and actually faster at the isotropic point as compared to the anisotropic point, telling us that eventually in the thermodynamic limit, the peak is always at the isotropic point. But most importantly, that we are still seeing superdiffusion and not diffusion on these system sizes up to 100 at significant perturbation strengths. So the conclusion here was that this superdiffusion seems really robust against perturbations that preserve the SO2 symmetry of the model and seems most robust in some sense of all kind of different type of transport that we see in these integrable models. And this must be related to the kind of inability of, or these giant magnons not being scattered on this type of perturbations. Yes.
So I'm coming back to my previous question. So in that case, it looks like the superdiffusion exponent depends on some Kepling constant, right?
Indeed, in this case, the superdiffusion depends on as it's written here in the inset, depends on the kind of the perturbation strength and also the diffusion, the anisotropy, and indeed is somehow this universal, what people call KPZ, 3/2 only in the absence of perturbations, but then it's smaller. Yes?
So how much should I really trust that, in the sense that, I would expect that you get like maybe some mixture of diffusion and subdiffusion. Like if I have a sum of two power laws and I fit it with a single power law, it will look like some intermediate thing.
So you're saying, I mean, so you're saying how much is really diffusion and how much is...
Well, yeah, if you see some continuously changing power, a possible interpretation would be that it's really supposed to be a sum of two power laws with like coefficients that change continuously, and it looks some intermediate thing when you fit it. Is that consistent with your data, or is it really somehow better fit by a single exponent that happens to be changing continuously?
I mean, it's so, okay, I think I don't have here this data. So, because of course, I mean, this is like, okay, eventually in the thermodynamic limit, again, this should saturate to some very large diffusion constant and essentially diffusion. So it should be a fact that is there only on finite systems, or equivalently in closed systems on finite times. I mean, it's just another... So in that sense, it's probably one interpretation is that, I mean, as I have this boundary-driven case, part of, I mean, the way I see it, that part of it goes through somehow without scattering as super diffusive, and maybe part of it is like diffusive. It could be in sense of what you're saying, that it is a bit of a mixture, which, yeah. Yeah, it is to stress that this is something that is on finite, I mean, is a finite size effect or finite time effect, but it's just extremely robust as compared to, let's say, ballistic transport or this diffusive integrable transport that we discussed before.
I see.
Good. Yeah. So, wait, I somehow went out. So somehow here at this point, so I would like to kind of conclude this transport part, and once again kind of highlighted the two conclusions that we had, and essentially that was this non-perturbative nature of the diffusive transport in Heisenberg model, and kind of the robustness of super diffusive transport to symmetric perturbations. And I mean, if there are no further questions, I would kind of change the viewpoint a little bit and discuss this other question of thermalization or absence of thermalization and equilibration of perturbed integrable systems. So as I already mentioned in the beginning, integrable systems or the equilibration of integrable systems is special because of this extra conservation loss prohibiting equilibration in purely, let's say, isolated system. And in this case, kind of what happens is that locally, such integrable systems equilibrate to a state that is described by a generalized Gibbs ensemble with kind of additional Lagrange multipliers, which are set by the state after the excitation through the condition that all these conservation laws are conserved and are somehow the same just after the excitation as in the steady state. And we know kind of how the story goes as when we add integrability breaking is that, I mean, and here I mean static integrability breaking. So since the full Hamiltonian is not integrable, what will happen is that, let's say, at very long times, the system will eventually locally thermalize and become thermal now with respect to the full Hamiltonian. And here, somehow, essentially, still at short times, this integrability breaking can be neglected. And this rather kind of order 1 times. Still, the system is locally, locally described by a generalized Gibbs ensemble. So as if it was integrable, and kind of same as I explained before, with Lagrange multipliers given by the initial state. And what we somehow showed already now a few years ago is that situation gets much more interesting once we add some weak dissipation, such that the integrability breaking is not coming due to the static perturbations, but due to driving and weak coupling to baths. Because essentially, in that case, we know that in such an open driven dissipative system, we'll have, again, a steady state that will be given or fixed by the baths. But the interesting part of it is that this steady state is not just of arbitrary form, but is at least can be approximated once again via generalized Gibbs ensemble. Now, with the difference that these Lagrange multipliers are given by the bath or the perturbations themselves, because as we said, bath fixes the steady state, and it fixes it to such a state in which now all conserved quantities must be stationary, so given by such essentially stationarity equation or condition for all conserved states, conserved quantities. So as if, like, for a generic system, it's easier to think. So you have a thermalizing system weakly coupled to bath. That's why at long times we'll have some temperature establishing, which depends on exactly which baths are you coupling the system to. Now, in such an integrable system, you have just more of such conditions and more such generalized temperature or generalized Lagrange multipliers to describe the state. And somehow, in our recent attempts, we were somehow thinking, okay, how to characterize this more exotic steady state and how to give some, let's say, compact and elegant description of them. And somehow with Markus Schmidt, who's also in the audience, we more generically thought of how to also use neural network to capture the what we call local complexity of states. So the complexity that we can measure, that we can detect by local measurements. And for that purpose, we kind of thought of autoencoders, because they can essentially characterize or get the intrinsic dimension of the data and can provide, let's say, a compact or compressed representation. Okay, so what an autoencoder does is that it takes some initial state and then it tries to, initial input, and it tries to reproduce it by going through a bottleneck. So, okay, it's such a neural network architecture that's shown here. And this reproduction of the output being equal to the input will be successful only when here in the bottleneck, in the latent space, we have at least that many neurons as is the intrinsic dimension of our input or of the data. And okay, in our case, now if you want to apply this to quantum states, we thought let's do time evolution in presence of some Hamiltonian and weak coupling to baths or some noise to make a connection to this problem we are studying. And then we do this again with tensor networks because it's very suitable and doable for such open systems. And then at long times plug these measurements into our autoencoder. So each data element will be a collection of different measurements for, let's say, one run, and then different the whole data set will be contained with different runs, let's say with same Hamiltonian, but slightly different couplings to baths. And here's the result. Now, when we compare how well kind of this reproduction matches the input, which are in this case now these local measurements, we see that for the evolution, which was done with respect to a chaotic Hamiltonian in the presence of coupling baths, we need essentially just a single neuron in the bottleneck related to the fact that the steady state can be approximated with a thermal ensemble, characterized with this one parameter, which is essentially temperature. So what we learn here is that, okay, with these autoencoders, we are able to extract kind of the number of parameters that our data is parameterized with. And this will be in case of weakly open chaotic time evolution, essentially just the temperature of the state at long times. And this is also seen in the latent representation, which is, let's say, a compressed representation of these different input measurements into some lower dimensional space, where these different, each of these runs corresponding to different temperature will be ordered with respect to the temperature. So indeed, we'll see that the latent that our latent representation is featuring the fact that at long times we have just thermal states. Interestingly, like let's say secondary direction related to the information in the second neuron will pick whatever common information, will pick the common features of the bath or the correlations that the baths are imprinting in the system. Now, when we contrast evolution with respect to chaotic versus integrable Hamiltonian, here as the dominant part, we see also from this autoencoder analysis that we clearly need more variables in the latent space to successfully describe the data, related to the fact that we are indeed stabilizing these more complex states, which are the generalized Gibbs ensembles.
You have time here in your picture at the top. Have you seen how the number of latent variables that's required varies with time? Can you see how it decreases as you thermalize?
Yeah, so I don't have it here. Like, for example, we did apply it also to, in that case, it was like random unitaries with some symmetry, like magnetization conservation. And it gave us access to seeing, for example, this bottleneck of the that Tibor was talking in his space. So it can detect kind of local complexity similar to, let's say, operator entanglement entropy that would be obtained from some tensor network. Yeah. But it's a bit limited in the sense that you need to, if you start your time evolution with some simple states, a low dimensional manifold, then this sets the bottleneck to the problem. Unless you introduce some randomness like this coupling to bus, then it should be fine again. But yeah, in principle, it is also able to detect the time-dependent, let's say, growth and then eventual decay due to the hydrodynamic. Yes. Okay, for most of all, so here we see that it can be used as a way to detect the complexity of the state. And somehow as the next which is good. So now we have a tool essentially to tell us how many parameters or so we need to characterize our state, and to distinguish the evolution of an ergodic versus integrable system. And in the last part, we were now going after an elegant or very, so trying to understand which are, how to add, let's say, iteratively, really the most necessary conservation laws in such a case. So how to distinguish which conservation laws are the most important ones, or which are the ones that the baths in this case are picking up and preferring in such steady states of open systems. And here I go back to a bit the cartoon I have and say that, okay, we should remind ourselves that when we take such an integrable system and weakly coupling it to bath, the bath will take it to the steady state approximately described by these generalized Gibbs ensembles. And not only the steady state, but also the time evolution will be given by time-dependent generalized Gibbs ensembles, where this evolution of these generalized temperatures or Lagrange multipliers can be extracted by using some sort of super projector, which weights essentially introduces tangential modes in this GG manifold and gives, let's say, a weight to how much I'm changing. I'm flowing along each of these slow modes, which are the tangential modes in the moment. So, let's say in the moment you are in a GG, and then it just asks how much do I move along different d rho over d lambda modes. And this is essentially then given by that expression, which tells us that, how much a Lagrange multiplier or how much flow I will be having along each of these directions is given by that scalar here. But now one can even use that to propose an iterative approach of how to find these steady states very efficiently. Suppose that you just started with the first guess, which was a thermal state. Now, it's very natural, of course, when I add more possibilities, more conservation laws in the description, I will have, in a sense, a flow along each of them. So the corresponding Lagrange multipliers will change. And the ones that will change the most are the most missing in my description. So that's why, as a next conservation law, I just take kind of a linear superposition of different conservation laws I neglected with the weight that is somehow proposed by my baths. And then I take this as my next conservation laws, plug it in with this GG with two conservation laws, and iterate it. Of course, here I have also what are these conservation laws that I'm making linear superpositions of? They can be, if I have no clue, I can add just a diagonal projections onto the eigenstates of the Hamiltonian, or I take some, if I have more clue, I can take the local of quasi-local quantities of the model. And then I will compare how good is my, let's say, truncated GG by comparing it to the diagonal ensemble. So I should kind of wrap up soon, but yeah, we see that, for example, when we do this for Heisenberg model, if we, let's say, we say that we don't have much clue, and we will just take the diagonal, as our basis on which we are spanning our better conservation laws to be the diagonal ones, we see kind of convergence shown on the lower panel. So this is just results for different system sizes. So maybe let's just focus on the biggest one. we see kind of, the error we are making with our truncated ensemble kind of goes down significantly. But what is nice is that if we compared what error we had if we just included the more easy local conservation loss of the model, it would be way worse than in our iterative procedure. So we can easily outperform, let's say, the other more naive approaches to find this steady state. And if we do the same kind of for transverse field easing, which has only local conservation loss, and we again compare what is the error depending, so here I'm plotting the error as a function of number of local conservation loss included in the description. I will see that, if I span out my space of possible conservation loss and make a linear combination of them, essentially in 2 iterative steps I'll be done. And this really significantly somehow reduces how hard it is to find these steady states, because we need to solve less linear coupled equations to find these Lagrange multipliers. And this should be kind of decisive when we try to scale this to thermodynamic limit. With this, let me conclude and somehow, first acknowledge my collaborators and also especially my postdoc, Soro, and PhD student Iris in Ljubljana. Kind of stop here with the conclusions. Just reminding you that we looked at these transport properties of perturbed integrable systems and see that actually in the presence of dissipative integrability breaking perturbations, we are able to stabilize interesting states even if we don't have purely integrable models. And so let me kind of stop with the advertisement that there are several open positions in my group. So if you have some good students or some interest, please write to me. Good. So let's stop here.
We have time for a few questions. I was wondering if you had any follow-up planned on the autoencoder part. Like, could you do further analysis of like what was learned in the autoencoder, like in the actual weights that were learned, and also can it be applied to, say, actually be a tool to truncate the state while sort of preserving the most important latent features?
Yeah, so what we are doing now is that we are kind of learning the Hamiltonian assisted by here, because essentially this latent space ordered things essentially with respect to the energy, and then this can help us learn which is the Hamiltonian. Suppose you didn't know where your thermal states are coming from. So that's somehow what we are doing. And it would be also very interesting to, let's say, maybe detect the hydrodynamic equations of motion, some sort of equations of motions in the latent space. So that's more for future.
Great.
Maxim?
Okay. Maxim?
If I'm allowed to ask a question, you showed early 2 different diffusions. What other sort of physical observables would tell maybe, not a quantitative but qualitative difference? So, if you have a quantum simulator and you want to, again, tell apart one diffusion from another, is there some other, observables which would be, again, much more, signature is going to be stronger, right? Maybe some are going to be 0, some non-zero, and so on, right, between these 2 limits.
Mm-hmm. I don't know how to formulate, but because one transport is dissipative and the other is not, so some sense both are diffusive, but in the integrable limit you have no dissipation in some cells. It's ballistic transport right through, but that sums down together to be diffusive. So I don't know how to measure this absence of dissipation. I don't know in this moment.